It's on the right-hand side, yeah. So f of 2 plus f of 3, f of 4, f of 5. Each rectangle intersects the curve on the right endpoint of each subinterval. So from x equals 1 to x equals 2, the first rectangle will intersect the curve at x equals 2, and its height would be given by f of 2, right? So base of 1 times the 21. F of 3 would be radical 25 minus 3 squared. That's 25 minus 9, which is 16. Square roots of 16. Be 25 minus 16, which is 9. Square root of 9 is 3. F of 5 will be root 25 minus 5 squared. That's 25 minus 25. 0 squared of 0 is 0. Oh, that's weird. There's no rectangle on the very end. The height of the last rectangle is 0. If I have this given function graphed up on the television screen, and I'll share my screen so everyone online can see it. When I do right endpoints, different rectangles. From x equals 1 to 2, 2 to 3, 3 to 4. 1 from 4 to 5, if I use the right endpoint at x equals 5, its height is 0, so there really is no rectangle. That's not okay? So, using calculator next. We'll do 1 times square root of 21 plus 4 plus 3 plus 0. I got about 11.58. Is that roughly what we should have? Yeah. It's good according to what the key said that I put up there earlier. 4, 5, 6. Going back to the television screen here. Would that be an underestimation or an overestimation of the area under the curve from the top? Under, right? Because I'm not accounting for these white spaces that aren't filled up by the green. I'm leaving area on the table that's not covered up by those green rectangles. How can I get a better approximation? Make more rectangles, right? An infinite number of rectangles. Where's the first rectangle going to start? From 1 to 2 runs the first rectangle, but if it uses the left endpoint, it will start with which value? What's that? These are left endpoints now, I'm sorry. So if I start from 1 to 2, the left endpoint would be 1. Each base is 1. This first rectangle intersects the curve at x equals 1. So f of 1 represents the height of this first rectangle. Base of 1, height of f of 1. Then from 2 to 3, that rectangle has a height of f of 2. Third rectangle runs from 3 to 4, so its height is f of 3. The last rectangle runs from 4 to 5. 25 minus 1 squared is 25 minus 1, or root 24. Evaluating the function 25 minus 2 squared is 25 minus 4, or 21, so that's 21. F of 3 and 4, I think were the same 4 and 3 we had earlier. F of 3 is 25 minus 9, which is 16. Radical 16 is 4. F of 4 is 25 minus 4 squared. 25 minus 16 is 9. Square root of 9 is looks like 1648. Yeah, perfect. Left endpoints, right endpoints. Strictly speaking, back on the screen. The last one, the right endpoints were an underestimation. This would be what? Overestimation. Because we have a concave down curve, these left endpoints produce rectangles that are above the function. So I'm including more area by the rectangle than our midpoint. I need the midpoints. So if the first rectangle runs from x equals 1 to 2, and I intersect it between those two in the middle, the rectangle's height would be given by f of 1.5. 1, still the common base length, times f of 1.5, f of 2.5, 3.5, and 4. 1.5 is the midpoint of the first interval from 1 to 2. 2.5 is the midpoint of the second interval from 2 to 3, and so on. All right, this one I don't know if I can do in my head, so I might need a little help from the calculator. I don't know what 1.5, 2.5, 3.5, and 4.5 squared all are. So let's do the square root of 25 minus 1.5 squared. That's 4.77 approximately. I'll need 2.5, 4.33. .57 for rectangle. The midpoints, and 4.5. 2.18. What we're going for is a picture that looks somewhat similar to this on the screen. Midpoints. Midpoints are, generally speaking, better than left or right endpoints because each rectangle kind of has the same shaded area above, that's the overestimate, as it would not shaded as an underestimate. This kind of, that's the whole world. How much we're approximating under by is how much we're also over approximating. Back on the calculator, I'm going to need this value plus this value value and the file value 14.85. Right. Trapezoids are a little bit different. We're going to stack trapezoids that look somewhat like this. Base 1 and base 2 are the parallel sides on the left and the right. Behind the height or length between the two bases is the height. What's the formula for the area of a trapezoid we've used so far? Yeah. Half the height times the sum of two bases. It's derived from parallel. The first and last base are bases of how many different trapezoids in the interval. The first and last are bases of how many different trapezoids? Just one, I think, right? At x equals 1, it's a base of only the first trapezoid. At x equals 5, it's a base of only the final trapezoid. At x equals 2, 3, and 4, each of those respective bases are bases of how many different trapezoids along our interval. So to make this a more efficient process, let's take 1/2 the height of 1 times the summation of all these different bases, keeping in mind that some double up and some do not. The first and last bases are bases of only one trapezoid. Every intermediate base is a base of exactly 2, because it's stacked and shared as I go from left to right. So we're going to do f of 1 plus 2 f of 2 plus 2 f of 3 plus 2 f of 4, and then lastly f of 5. It's actually going to be 5 function values. This is where I got goofed up yesterday. I didn't actually include the 5th number. From x equals 1 to x equals 5, there's going to be 5 different values. 1/2 of 1 is 1/2. F of 1, 25 minus 1 squared is root 24. 2 times f of 2, that's the square root of 25 minus 4, which is 21. F of 3 would be 25 minus 3 squared, which is 25 minus 9, 16 squared is 29. Square root of 16 is 4. F of 4 is the root of 25 minus 16, which is the square roots of 9. Or 2 times 3. F of 5, once again, was a 0. That last trapezoid really just looks like a triangle, because the last base really isn't there. It has no height. Going to our calculator. We'll need 1/2 times square root of 24 plus 2 square root of 21 plus 2 times 4, which is 8, plus 2 times 3, which is 6. And I don't need the last one because it's adding on nothing. 14.03. Outstanding. Generally speaking, these trapezoids are preferential over rectangles because that top leg of the trapezoid follows the average rate of change in the function throughout the interval. So as I can kind of see here, from x equals 1 to x equals 2, this leg generally follows the rate of change in the curve from x equals 1 to 2. This next leg generally follows the next rate of change in the curve from 2 to 3, and so on. From 3 to 4, this leg is a good approximation for the rate of change in the curve on that interval. Not a lot of error, not a lot of over or under estimation, at least until you come to this last one. What are our thoughts here, guys? Everyone feeling all right? Using rectangles and trapezoids to approximate areas under curves? All right, then. Let me have you get your laptops pulled up, and we'll get you some work on Schoology. Shay, I have your quiz graded too. I just put that at Infinite Campus this morning. Whenever you're back in class, I can get you your copy.
Okay, thank you.